Now let's look at the linked list implementation of this data structure, which is for managing the list of process and free list. Assume that this is the memory and it has got some part of OS, and from here we have got the free list, right? So assume that at some point in time the memory is occupied like this. From 0 to 99 it is occupied by process, and again from 100 to 199 let's say it is free, and from 200 to 299 it is occupied by a process, and from 300 to 399 is free. See, these numbers are just random numbers, I just picked them to have easy representation. In general these numbers will be very big, from 1k to 2k, something like this. Fine. So anyway, how does this linked list work is, we are going to maintain a linked list which will have this structure. The structure of an element in the linked list will be like this. So it will say whether this particular memory, for every block of memory it is going to have this, whether this block of memory is either occupied by a process or is it a whole, which means it is going to say whether it is a process or a whole, and then it is going to say what is the starting of this and what is the ending of this, right? So using this structure, which means like this, we can say that whether we can find out what are the holes in the memory. For example, for this memory representation, for this instance of memory, we'll have the linked list representation like this. See this? Now if you look at the first part, this part of memory, it is starting from 0 and it is ending at 99, right, and is occupied by a process. This will be pointed by the head. So the beginning is going to be like this, and now it is a linked list, right? So linked list means from one node we are going to have the pointer to the next node. So, and the next node is just a whole and is starting at 100 and is ending at 199, and the next one is a process and is starting at 200 and is ending at 299, right? And the next one is a whole it is starting at 300 and it is ending at 399, right? So compared to that bitmap, this one has some advantages, in the sense searching will not take a lot of time. You need not search for a contiguous this run of zeros, and moreover, depending on the number of holes and number of process occupied, which means depending on the number of contiguous blocks, the number of nodes in this one will depend. So on average, by simulations they found out that the memory required for this linked list is less compared to the memory required for the bitmap, where the allocation size is 4 units. Allocation units are 4 bytes. On average they found it out using simulations, right? Now, is this enough or should we do any modifications? See, there are various ways we can allocate and deallocate the nodes in this. So one way is, whenever any process is created, you can go and add it at the end, or you can go and add it at the beginning. So actually adding a node at the beginning of a single linked list is easy and straightforward, because you can create a structure here, a node here, and that node will point to this and the head will point to that. In a constant time we can add any node. Okay, in a single linked list which is having only the head pointer, in data structures I'll show you that inserting an element in the beginning of the list is very straightforward and simple. It takes order of 1 time, but inserting an element at the end of the list is going to take order of n time, because we have to traverse the entire list and go and add it at the end. Got it? So what I mean to say is, this linked list implementation is better, but then how are you going to represent the nodes? That is going to have a significant impact whenever you want to delete a node, or whenever you want to insert a node. So it is found out that it is better if you maintain the list in an increasing order of the starting addresses, which means like this, in increasing order of starting addresses. Why it is useful to maintain a list in the increasing order of starting addresses is, in case if any of the process vacates, if any of the process is pulled back from its current location, then merging the neighbors to make it a big whole is straightforward and easy. For example, watch it. If I am maintaining the list in the increasing order of this starting addresses, in case if this process is pulled out, which means if this one is brought out, then what happens is 200 to 299. If this one is brought out, then this will become a whole, fine. This will become a whole, perfect. But if you look at it, there is a hole before it and there is a hole after it, right? Therefore, these two holes can be merged with this hole to make it a big hole, isn't it? So what we could do is, whenever we are pulling it out, it is not just enough that you make it as a whole. You have to observe what is the next one. If next one is a whole, you merge with that, right? And if previous one is a whole, you merge with that. So first point is maintaining it in the increasing order of starting addresses is going to be beneficial in the sense, whenever we pull out a process, we can merge it, and moreover, maintaining it as a double linked list is useful, instead of single linked list. The reason is, if you have a single linked list, you can observe what is the hole next to you and whether it is a hole or a process, and then you can combine it, right? But if you have a double linked list, you can even observe what is the block which is ahead of before you, and in case if it is a hole, we can merge it, right? So in this case, maintaining it like a double linked list is going to be useful. And once you maintain it like a double linked list, now whenever you free up this process, you can understand that, oh, before also it is a hole and after also it is a hole. Now everything can be combined into a single hole, isn't it? And now we can say that the single hole is going to start at 100 and is going to end at 399. Therefore, it is very easy in order to merge the holes. So maintaining this list in the increasing order of the addresses is going to be useful, and as a double linked list is going to be useful in most of the cases. Now let's see what are the algorithms that we are going to use on these data structures, especially this linked list, in order to find out the holes and assign it. See, one more thing. Now we are going to discuss about the algorithms. So when I am talking about these algorithms which are used to find out the holes and assign them to the process, there are various strategies, and these strategies can be applied equally well either to the fixed partitioning or to dynamic partitioning. But then I'll talk mainly about the dynamic partitioning, because even though we can use them for fixed partitioning is rarely used, very rarely used, right? So from now on, I'm going to focus on dynamic partitioning, but remember that these methods could be extended even for fixed partitioning, right? So now I'll take each algorithm and I'll show you how this linked list can be used not to implement the algorithm, and we shall find out the time complexity required and everything, all the properties, right? So my intention is to focus on dynamic partitioning, even though it can be applied for fixed partitioning as well. So, and my intention is to focus only on the linked list, not on the bitmap, right? Fine.